Okay, the name of the next problem is physical pendulum. The question is, what is the frequency or angular frequency of the physical pendulum, or what is the angle at a given time as a function of time? We can generalize this problem for an object where, consider this an object. If I pull this up slightly and release it, it will start to oscillate. And that object can be anything as long as it is pinned from some point, not through the center of mass. It's going to oscillate. We can generalize this and find the answer as a function of moment of inertia. But for this example, let's assume a bit more simpler case. If we can solve this, we can solve anything. Consider a rod of given dimensions, which is pinned here, which is free to rotate about that pin. And it's a perfect rod. And the parameter of the rod is m is for the mass, and L is the total length of the rod. And if we disturb this rod, namely if we rotate this slightly, slight means that theta is small angle approximation is going to be considered here, and release it, it will start to oscillate. The question is, what is the frequency, what is the relation, etc. So in order to study that problem, we need to draw the free body diagram. This is the free body diagram. We can use the same figure. Here is the only force that is acting on the rod externally, mg is the weight, and there is also force acting on the rod through the pin. However, we can draw the direction of the force acting on this rod through that pin. However, it won't have any effect as far as the angular momentum, angular acceleration is concerned. If I define my direction of the angle in that direction, so this is the positive direction. And the equation of motion then, not linear but rotational, can be written as torque is equal to I times the moment of inertia times the angular acceleration. Torque then is equal to mg times the perpendicular distance. Okay? The perpendicular distance is this distance, which is L divided by 2. L divided by 2 is that distance, multiplied by sine theta. Let me find I over there. Then we'll continue to write the equation. I for rod through the center of mass, which is the center of the rod, is 1/12. It can be either a separate question. It is 1/12 L square. But we need to write that moment of inertia with respect to that point. Let me call this point A. Then I rod with respect to point A is whatever the moment of inertia for the center of mass plus, using the parallel axis theorem, m times whatever the distance to the center of mass, which is L over 2 squared. So you add these two quantities and you end up with 1/3 ml square. So that is 1/3 ml square, which is I, times alpha. Okay, let me write this angular acceleration. You also have to think about the direction. Note that we chose that direction to be positive. In that case, the direction for the torque, it will tend to rotate to the opposite direction. And this is pulling down, so it will try to move the rod in the opposite direction. and this is negative. Okay. And alpha is the second time derivative of the angular acceleration. Small angular approximation means angle approximation. Sine theta is approximately equal to theta. So m cancels m, one of the L goes away. Negative g, sine theta is theta, 1 over 2 coming from over there is equal to 3L theta double dot, or theta double dot is equal to, so 1/3, is equal to negative 3/2 3g divided by 2L theta. And that is the kind of equation that we see over and over whenever we study oscillation. The second time derivative is linearly proportional with a negative coefficient to itself, which means that this is equal to angular angular frequency squared theta with the definition of square root of 3g divided by 2L. Okay? And the solution for that differential equation is, as a function of time, can be sine omega naught t, or can be cosine omega naught t. Both of them are solutions, and it's a linear equation. So the linear linear combination is also a solution, which is the general solution. Okay. And A and B are found using the initial condition. Initial condition is, what is the initial value of theta? You pull this slightly up, say 1 degree. And the other initial condition, what is the initial velocity, initial angular velocity of the system? If you release it from rest, then the initial angular velocity is going to be 0. You have two unknowns and a set of initial conditions. You find A and B accordingly. So that's the end of the question.